All right, let's start with chapter 2. In this chapter, we'll discuss a little bit more detail about the structures of the atom. We'll discuss a bit about the periodic table itself. This will lead to better knowledge to help prepare you for discussing electronic configurations, bonding, and then chemical reactions in the future. So, the first section discusses a bit about the history of our development, or the development of our knowledge of the atom, its structure itself, periodic table. And again, I don't ask specifics as far as who did which experiment, but understanding these basic experiments, helps you in visualizing better the atom itself and comprehending why the periodic table is shaped the way it is, how it came to be, and even in comprehension, if you look at different texts, they reference different group numbers, as we'll mention. So it's good to understand why there are a couple of different ways of referencing group numbers. Now, early on, people who knew about cathode rays, well, they called them cathode rays, did not know really what they were at first, but that they could be deflected by positive and negative electric fields, and that these cathode rays are attracted by a positive electric charge. So, and in fact, Robert Millikan developed an oil droplet experiment, in which case, really very, very small charged oil droplets were falling in an electric field, and he could determine from this what the smallest electric charge actually is, which helped us understand better the electron itself. This sounds kind of silly when we think about it now, but the plum pudding model was a popular theory as far as how matter itself is arranged, how it's composed. Now, think about a bowl of pudding. It's fairly even consistency throughout. Plum pudding has little bits of plum flecked throughout, and that's the way people thought of matter. You take a chunk of lead, and the mass itself is spread out very uniformly, and these electrons we were now aware of were bits and pieces spread out throughout this plum pudding. And people also knew about radioactivity. At least different types of radioactive particles are spontaneously emitted from certain types of matter, certain unstable radioactive isotopes, or radioactive materials at the time. Didn't know about isotopes. Two types of radioactive particles that we were aware of. Let me change this to beta particles. And these are really just high energy electrons, which are also ends up being cathode rays. And alpha particles, as they were named, and we now know that these were actually really is the nucleus of a helium atom. So, but these two particles, we combine this information. Rutherford set up an experiment to use alpha particles and try to figure out how do they interact with matter. Again, this was before they knew what these particles were. So he shot a beam took a radioactive source of alpha particles, ran it through a little lens to slits to focus it, and took a piece of gold and hammered it out where it was so thin that we now sort of estimate he probably had it to be about maybe 20 or 30 atoms thick, so a very, very, very thin film of gold. And he expected the alpha particles, for the most part, to go straight through. He expected something to be bent, sort of like this. He really expected it to act more like when we have light going through a piece of glass. Light going through a window pane that gets refracted and bent slightly. And that's what he expected to happen. But that's not what happened. As this shows, some of these particles, the alpha particles, actually bounce back the direction they came from, which completely stunned scientists at the time. It's not at all what they expected. But that led to our current understanding of the structure of an atom, or first the atoms exist at all. This is the plum pudding model, where the mass is spread out evenly throughout the atom itself, and these electrons are just spread out within this plum pudding. But since we have these alpha particles that come through, most of them pass straight through, but when they actually happen to hit the nucleus, they bounce back. It's like a BB hitting a bowling ball. And this because the alpha particle is very small relative to the gold nucleus, which we now know. So that's why these particles bounce back, because you're hitting a very large object. But it's a very large object that occupies very little space. So again, more alpha particles will go straight through, but if they happen to hit this small nucleus, then they get bounced off. And this leads to our more modern understanding of a structure of an atom. So the nucleus itself, we now know, is positively charged at the very center of the atom, and it contains most of the mass of the atom. Over 99% of the mass is in this very small nucleus. And in fact, this nucleus is about 10,000 times smaller than the radius of the atom itself. and the nucleus consists of two types of particles, or two main types of subatomic particles. One is a proton, which is positively charged. The other is a neutron, which is neutral, which kind of goes along with his name. In addition, protons are what defines the element itself. All atoms of a given element have the same number of protons, which we'll discuss is the atomic number. That's what defines a particular atom. Electrons, on the other hand, we now know are negatively charged particles. They're roughly 2,000 times smaller than the mass of the, will have 2,000 times smaller mass than that of the neutrons and protons. So it's not insignificant, but still they don't account for much of the mass of the atom itself. These are located outside of the nucleus of the atom. They're found in what are called electron clouds or orbitals. The location of the outer electron is what determines the radius of the atom itself. And in fact, the nuclei and the electrons are so small, most of the atom is really just empty space. There's nothing there. It's just a vacuum. This shows an example of the atom of our current understanding. In the center, we have a very, very small, dense nucleus. That's where, again, most of the mass of the atom is located. Outside of this, this shows this hazy region, which is the electron cloud. It's called that because electrons don't exist around an atom in distinct orbits like planets around the sun. That's the way people first tried to describe electrons, but that's not the way they really exist. They can be found in some region. We know probably where they're found, but not exactly. So we kind of have this cloudy region of probability where we think we can find electrons. But they're moving about all the time, random directions, so we don't know where they are exactly. But the term orbit for planetary orbit is sort of a legacy, so we use orbital instead. Similar, but remember, it's not the same description as, it doesn't mean the same thing as orbits of planets around the sun. We'll discuss later in the next chapter a little more about the shapes of these orbitals. And this just shows a blow-up of the nucleus, of course, where it's just composed of lots of tightly packed protons and neutrons. So I also want to discuss here atoms versus ions. Atoms are electrically neutral. Atoms of any atom are neutral, which means they have the same number of protons as they do electrons. Protons and electrons have the same equal and opposite charges. Ions are formed whenever atoms have gained or lost electrons. Remember, electrons are negatively charged, so if you gain an electron, you actually get a negative charge. Cations, therefore, that have lost electrons now have a positive charge. Anions, on the other hand, have gained electrons, so they have a negative charge. And as far as masses of atoms, we often discuss these in terms of atomic mass units. Sometimes they're called Daltons. I've really rarely ever used the term Dalton, but some texts use it, some professors use it more often. But atoms are so small we can't really measure them on scales. So we use this relative unit of mass to compare one atom to another. It's called AMU, and the way we define an AMU is we take basically a specific carbon atom, and it's 1/12 of that carbon atom's mass. So we can measure the mass of a large sample of carbon atoms and extrapolate or interpolate and figure out the mass of one atom itself. And so basically, though, if you think about it, one AMU, 1/12 of a carbon atom, it has 6 protons, 6 neutrons. So 1/12 of that is an AMU. So an AMU is about the mass of a proton or neutron. But we can't measure individual protons or neutrons. It's just using this carbon atom is much easier to use as a standard for making a very, very accurate mass comparison. So again, this shows sort of break down this information. This notation we'll discuss in a couple slides actually is called isotope notation. The masses, you don't need to remember these, but again, the mass of a proton and neutron, they're almost identical. And we'll discuss a little bit about how these compare to the mass of the atom in a bit. But their mass number for both these is 1. And this is a bit of a confusing aspect with terminology, so you got to be careful with some of the terminology. Mass number isn't the actual exact mass of the atom. It's really kind of an approximation. It's really, if you add up the mass number, you get the sum of protons and neutrons in a nucleus. So it's very close to the real mass. But if you compare the mass number of 1 to the actual mass of 1.00867, they're close to the same thing but not exact. But we'll use this discussing isotopes in the next couple slides. You'll see a little bit better why we use that. And the exact mass, I don't care if you memorize this. We'll do some calculations later. You can figure it out in the next chapter, but or the next couple sections. But they're just very, very, very small masses. You should know the charge, or the relative charge. Neutrons are neutral, protons +1, electrons -1. Actual charge is in coulombs, and we'll touch on we won't touch on this in this class. We'll touch on that more in 105 and 6, and talking about redox reactions, electrochemical reactions. So anyway, it's a basic summary of the subatomic particles.